We're going to look at cardiac output and its control in this section. Cardiac output is really important. It's how much blood each ventricle pumps out per minute, and it's measured in liters of blood per minute. To calculate the cardiac output, you need to memorize this formula, so make sure you star this. Very important to know. So cardiac output is heart rate times stroke volume. And remember, the stroke volume is the amount of blood that the ventricle pumps out with each contraction or each beat. So here we have cardiac output. Let's say that the heart rate is 72 beats per minute. And let's say that our stroke volume is 0.07 liters per beat. So that would give us a cardiac output of 5 liters of blood per minute that each ventricle is pumping. And the total blood volume in an adult is just over 5 liters. So each ventricle will pump the entire blood volume in 1 minute. So that means that if you trace a red blood cell starting in the left ventricle, and by the time it gets back to the left ventricle again, that'll take 1 minute. So that's our cardiac output at rest, is right around 5 liters per minute. But of course, when we start exercising, we need to get more blood out to the muscles. So we actually will increase our cardiac output by increasing the heart rate and the stroke volume. And so we'll look at that here shortly. Okay, so 2 ways to regulate the cardiac output. We can change it by changing either the heart rate or the stroke volume. And the heart rate and stroke volume are going to be regulated by 3 things. So we've got the autonomic nervous system, parasympathetic and sympathetic neurons will innervate the heart. Endocrine system, the hormone epinephrine from the adrenal medulla will affect heart rate and stroke volume. And then we have something called autoregulation, which is just a property of the heart muscle itself. And this is called Starling's law, which we'll explain in a little bit. But it's not surprising that heart rate and stroke volume are being regulated by nervous system and endocrine system. So remember, these are the 2 that maintain homeostasis. This picture shows the autonomic nervous system innervating the heart. So in blue, you have the parasympathetic neurons, and they're going to be innervating the SA and the AV nodes. So parasympathetic will affect the heart rate. And then in green, we have sympathetic neurons, and they also innervate the SA and the AV nodes, so they also affect the heart rate. And then sympathetic also innervates the ventricle walls. So that will increase the contractility of the ventricles and will affect the stroke volume, because if the ventricle contracts harder, it squeezes more blood out with each beat, and that'll increase the stroke volume. I've summarized the autonomic regulation of cardiac output here. So you can see that both sympathetic and parasympathetic stimulation will affect the heart rate, and that will affect the cardiac output, the amount of blood that's being pumped by each ventricle per minute. And then the sympathetic nervous system is the only one that affects the stroke volume, because it innervates the ventricle walls and will increase the contractility, squeeze more blood out with each beat, and that will increase the cardiac output. So this is really important to know, so make sure you star this in your notes. So the sympathetic nervous system, if that's stimulated, it will increase the cardiac output. And that's important because if the bear is after you, you need to increase the cardiac output, the amount of blood that you're pumping with each ventricle per minute, and increase the blood flow to the muscles so you can run away or fight. So remember that sympathetic nervous system will innervate both the SA and AV nodes, and then also the ventricle walls. So if we stimulate the sympathetic neurons to the SA and the AV nodes, that will increase the heart rate. And if you increase the heart rate, if we look at our formula here, that will increase the cardiac output. So then you'll start pumping more blood per minute out of each ventricle. And to answer the question how the sympathetic nervous system increases the heart rate, that's just because it innervates the SA and the AV nodes. The sympathetic nervous system also innervates the ventricle wall, and so it will increase the contractility of the ventricles. So the ventricle will squeeze harder and also faster, and so you'll squeeze out more blood with each beat, so that'll increase the stroke volume. And if you increase the stroke volume, that will also increase the cardiac output. The parasympathetic nervous system does just the opposite. It will decrease the cardiac output because when you're resting and digesting, you don't need as much blood flowing around the body, so it will decrease the cardiac output. So the parasympathetic neurons, remember that they only innervate the SA and the AV nodes. So if you increase parasympathetic stimulation while you're resting and digesting, that will decrease the heart rate. And if you decrease the heart rate, if we look at our formula up here again, decreasing the heart rate will decrease the cardiac output. Okay, and then just to answer our question, how parasympathetic decreases the heart rate, it's because it innervates the SA and the AV nodes. And remember, the parasympathetic neurons do not innervate the ventricle walls, so they're not going to have any effect on the stroke volume. Okay, you don't need to know these pictures at all. This is just showing you what the sympathetic neurons do to the pacemaker cells and the SA node. They will actually depolarize their membrane potential. And then the parasympathetic neurons, their effect on the SA node pacemaker cells is they will hyperpolarize the membrane potential. So what we see in this graph here is we're just looking at the action potentials that are generated in the SA node pacemaker cells. So the gray line is just showing you at rest. You can see that pacemaker potential, you reach threshold, trigger the action potential, that will spread through the heart, and then hopefully we'll get the contraction, and then we start over again with another heartbeat over there. And you can see with sympathetic stimulation in green that sympathetic neurons will depolarize the pacemaker cells and the SA nodes, so the membrane potential is now more positive. So it's much easier to reach threshold and generate an action potential, and then the heart contracts. And so you can see the number of action potentials produced with sympathetic stimulation. We have more action potentials produced than we did at rest, which was in gray. So that'll increase the heart rate. And then in blue, you can see the parasympathetic stimulation will hyperpolarize the SA node pacemaker cells, so it takes longer to reach threshold. And so you're not going to generate as many action potentials, and that'll slow the heart rate down. Okay, you don't need to know this picture either, but it's just showing you that sympathetic neurons, they innervate the ventricle walls, and they make the ventricle contract harder. And that's because you end up releasing more calcium, and so you get more cross-bridge cycling, and so you get a stronger contraction, which will increase the stroke volume and increase the cardiac output. Okay, and this is just showing you kind of a nice flow chart, just showing you what affects the heart rate here at the SA node. And remember, both sympathetic and parasympathetic innervate the SA node, so they will both affect the heart rate, and that'll affect the cardiac output. And then only sympathetic will innervate the ventricle wall, and that'll affect the stroke volume, which affects the cardiac output. And then we also have hormones that can affect the cardiac output, and epinephrine. And remember, that is secreted by the adrenal medulla in response to sympathetic stimulation. So epinephrine is going to do the same thing as the sympathetic neurons, so it'll affect the SA and AV nodes, and that'll increase the heart rate. And then it will also affect the ventricle walls, that muscle there, make it contract stronger, and that'll increase the stroke volume, so you squeeze out more blood with each beat. So both increasing heart rate and increasing the stroke volume, both of those will increase the cardiac output. So we're going to have more blood being pumped out of each ventricle per minute, and so you'd increase the blood flow to the organs. Okay, there's three factors that affect the stroke volume, which in turn will affect the cardiac output. So the three things that affect the stroke volume, we have the ventricle contractility, so how strong the ventricle is contracting. And remember, that's from the sympathetic neurons innervating the ventricle wall, and then also the epinephrine released from the adrenal medulla. And then we also have the end diastolic volume, which we'll talk about preload and Starling's law. And then we have afterload. Afterload is just the pressure in the artery that the ventricle has to overcome to open the semilunar valves to eject the blood. We call it the afterload because it's a load placed on the heart after the ventricle starts contracting. So if you have maybe pulmonary hypertension, let's say, so you have high blood pressure in the pulmonary artery, the right ventricle is going to take longer to contract and squeeze and generate more pressure before it can actually open that semilunar valve. So you have less time to eject the blood. And so if you increase that afterload, you're actually going to decrease the stroke volume. So less blood is going to be pumped out with each beat, and if you decrease the stroke volume, that'll decrease the cardiac output. So here's just a summary of the 3 factors that affect the stroke volume. So I've got them over here on the right. So sympathetic stimulation of the ventricle walls will increase their contractility. The ventricles contract stronger. That will squeeze more blood out with each contraction. That increases stroke volume, which will then increase the cardiac output. And then we have the preload, which we're going to talk about in a minute. And then we have afterload, which we just talked about. So if you have high blood pressure in the pulmonary artery or the aorta, it's going to take longer to open the semilunar valves. You're not going to be able to eject as much blood. So less blood is pumped with each beat, and so that would actually decrease the stroke volume, which would decrease the cardiac output. So let's take a look at preload. Preload and Starling's law, this is just a form of autoregulation. It just means it's an intrinsic property of the cardiac muscle itself. So it's just a property of it that no outside influence, no nerves, hormones, nothing influences it. So remember when we talked about the end diastolic volume? That's the amount of blood that's in the ventricle at the end of diastole, so at the end of relaxation, right before the ventricle contracts. So if you put more blood into the ventricle, if you fill it up more, you're going to stretch the ventricle walls, and that'll stretch the sarcomeres in the cardiac muscle, and they will actually contract stronger than if they're not stretched as much. And this is because cardiac muscle is really different from skeletal muscle. So remember in skeletal muscle we talked about the sarcomeres being at the optimum length, and you always get the greatest amount of force being generated. But in cardiac muscle at rest, the sarcomeres are a little bit scrunched up, so they're a little bit too close together. So if you do fill the heart with more blood, you stretch those sarcomeres and they're going to contract stronger. And so if you increase that end diastolic volume, you're going to increase the preload. And the preload is just the pressure that's created on the ventricle walls by all that blood that's in the ventricle. We call it the preload because it's a load placed on the heart before it starts to contract. So you stretch it out before it starts to contract. And with the ventricles stretched, they will contract stronger. And so you're going to squeeze out more blood with each beat, which means you're going to increase the stroke volume. And if you increase the stroke volume, that will increase the cardiac output. So Starling's law, all it basically says is that if you return more blood to the heart, it's going to pump out more blood. Okay, and that's really important because if you're exercising and getting more blood flowing around and you're returning more blood to the heart, you need to keep up with that and pump more blood out. Okay, because if you didn't keep up and you didn't have Starling's law going on, then the blood would start to back up and then you'd end up in congestive heart failure. So this is just all Starling's law says, is that if you increase the venous return, how much blood is returned to the ventricles, you will increase the end diastolic volume, you're going to stretch the ventricles more. And with the sarcomeres stretched closer to their optimum length, they're going to contract stronger, and then that'll increase the stroke volume, meaning you're going to squeeze out more blood with each contraction. And this is the length tension curve for cardiac muscle. It looks pretty different than what we looked at for skeletal muscle. So on the bottom here we have the end diastolic volume, and then we have the stroke volume on the y-axis. So all it's just showing you is that if you increase the end diastolic volume here, so you go from here to here, if you put more blood into the ventricle at the end of diastole before it contracts, you're going to stretch the sarcomeres more, closer to their optimum length, and so they will contract harder and squeeze out more blood with each beat, and that'll increase your stroke volume. And then this is just showing you the effect of the sympathetic nervous system on the stroke volume. So if you're just looking at a particular end diastolic volume, whatever that might be, maybe it's 130 mils, and if you just look at increasing sympathetic activity or decreasing sympathetic activity at that particular end diastolic volume, you can see that the sympathetic nervous system does have an effect on stroke volume as well, because remember, it innervates the ventricle walls and will increase the contractility, so they'll contract stronger and pump out more blood with each contraction. Okay, so here's just a nice flow chart just showing you the 3 factors that influence stroke volume. So remember that we have our end diastolic volume, which is our preload. So if we're filling the heart up with more blood, then it will stretch more, will increase that preload, and the ventricle will contract stronger, squeeze out more blood with each beat, and that'll increase the stroke volume. And then remember the sympathetic nervous system. Okay, that will innervate the ventricle walls and make them contract stronger, so that'll increase the stroke volume too. And then if we decrease the afterload, so remember, afterload is just talking about what's the blood pressure in the pulmonary artery or the aorta, and if we can decrease the blood pressure in those arteries, then we can actually increase the stroke volume, because it's not going to take as much pressure in the ventricle to open up those semilunar valves, and then we can inject the blood sooner and for a longer period of time and inject more blood out with each beat, and that'll increase the stroke volume. So to answer our 2 questions down here, if you increase the preload, so if you increase the end diastolic volume, you fill the heart up with more blood, that will stretch it and make it contract harder, and that'll increase the stroke volume. But if you increase the afterload, so maybe the person now has systemic hypertension, so they have high blood pressure in the aorta, or maybe they have pulmonary hypertension, so high blood pressure in the pulmonary artery. So if you increase the afterload, it's going to take longer for the ventricle to generate enough pressure to open up the semilunar valves, and then it won't have as much time to pump out the blood. So you'll pump out less blood with each beat. So if you increase the afterload, that will decrease the stroke volume. Okay, and then just summarizing everything that we just talked about. Things that will increase the stroke volume would be increasing sympathetic stimulation. That'll increase the contractility. The ventricles will contract stronger, squeeze out more blood with each beat. That'll increase the stroke volume. If you increase the preload, so you fill the ventricle with more blood, it'll stretch the ventricle walls closer to the optimum sarcomere length, and the ventricle wall will contract stronger, and that'll increase the stroke volume, the amount of blood that's pumped out with each beat. And then if you decrease the afterload, so if you decrease the blood pressure in the aorta and the pulmonary artery, it's going to take less time for the ventricle to generate enough pressure to open the semilunar valves, and then the ventricle will be able to pump more blood out with each beat, so that'll increase the stroke volume. And remember, if you increase the stroke volume, you also will increase the cardiac output. And remember, cardiac output is how much blood you're pumping around per minute from each ventricle. Okay, and then lastly, I just wanted to talk about a problem with cardiac output, and this is congestive heart failure. So this is unfortunately very common. So if you have either ventricle not pumping blood like they should, their cardiac output has gotten too low, then we're going to have two problems. So the first problem is you're not getting enough blood out to the tissues, and that's going to cause some issues. And then also the blood's going to start backing up where it should not be. So let's take a look at if the left ventricle fails. So if the left ventricle is not pumping blood very well, think about the picture of the heart, and when we looked at all the pulmonary and the systemic circuit, and if blood is backing up in the left ventricle, it's going to back up into the left atrium, and then it'll back up into the pulmonary vein, and then it's going to back up into the lungs. And so we end up with too much blood and high blood pressure in the capillary beds in the lungs, and then that will push fluid out of the blood into the lung tissue, and we end up with pulmonary edema. And edema just means swelling. So the person will have problems with coughing, maybe they get short of breath, like if they go up the stairs or something, having a hard time breathing. And then if the right ventricle is failing and not pumping very well, if you think about the anatomy of the heart, if the right ventricle is not keeping up and not able to pump enough blood out, the blood will back up into the vena cava, and then that will back up into the systemic circuit and will cause two things. We can see ascites, which is when fluid builds up in the abdominal cavity. So because the blood pressure is too high in the vena cava, it pushes out extra blood into the abdominal, sorry, not extra blood, but extra fluid into the abdominal cavity, and you get ascites. It's a really weird feeling if you were to put your hand on this person's belly, and then if you tapped it with your other hand, you would actually feel a fluid wave. You could actually feel the fluid coming back and bouncing against the wall. So this person is not fat. This is just all fluid that's built up into the belly. This ascites can cause problems because it can push on the diaphragm, and then the diaphragm can't, when it contracts, it lowers down, and so then it has a hard time doing that, and so they will have problems breathing. And then also all this extra fluid pushes on the stomach and can cause some vomiting and nauseousness, so that can be an issue as well. With the right side of the heart failing, we can also get limb edema, so we can get swelling like in the feet, for example. And then this is just showing you a chest x-ray, and the heart is right here. The lungs should be all black. So black means there's air in there, but you can see there's these kind of patchy white areas in the lungs on both sides. That's pulmonary edema. So we have fluid that's leaking out of the pulmonary capillaries into the lung tissue, and that's going to make it very difficult to do gas exchange and to breathe. So we see pulmonary edema when the left side of the heart is failing. And the other thing to keep in mind is that the two pumps are connected to each other, okay, because you've got that series flow, you know, pulmonary circuit to the systemic circuit back to the pulmonary circuit. So if you have, for example, the left ventricle failing, blood's going to back up into the lungs, which then backs up into the pulmonary artery, and that's going to increase the afterload for the right ventricle. So then the right ventricle has to work harder to pump the blood around because the left ventricle is not keeping up, and then eventually the right ventricle will fail as well. So if you have one side that's failing, it oftentimes will cause the other side to fail eventually as well.